Hello, welcome to this video. This is 3-6, and today we're going to be talking about derivatives of inverse trigonometric functions, as well as on the back half of the lesson, be talking about higher order derivatives. Without further ado, I want to go ahead and I want to jump off where we left off in the inverse trig review lesson, and that is with example number 1, saying here, consider the function y is equal to sine inverse of x. And they want us to go ahead and find dy dx. This is going to serve as the proof for how we get our derivatives, which are listed below. But if I have a inverse function statement, I can go ahead and I can take the inverse of the inverse, and I can say, all right, well, sine of y, that is equal to x. Okay, and I want to differentiate this. So the derivative of sine, well, that is cosine of y, and I have to multiply times the chain, times the derivative of y, which is y prime, and then the derivative of x is equal to 1. So solving for the derivative, solving for dy dx, we get y prime is equal to 1 over cosine of y. Now, this doesn't really help me. It's not in terms of x. So what I'm going to go ahead and do is I'm going to use this right triangle here to the right, and I'm going to go ahead and take the information that was given in the problem. Sine of y is equal to x. Well, that is x over 1. This is x over 1. So if this angle here is y, then using SOHCAHTOA, I know that sine is the side opposite. So here's x, and the side that's the hypotenuse is 1. Here's 1. And I'm just missing this side down here. So using good old Pythagorean theorem, say I want to solve for this side, and I'll just call it a since we're already using x. I can say that a squared plus x squared is equal to 1 squared. And I'm going to go ahead and I'm just going to solve for a. A squared is equal to 1 minus x squared. And if I take a square root, we get a is equal to the square root of 1 minus x squared. And again, I'm only going to use the principal square root because this is a side length. So this side is 1 minus x squared. Okay, cool, Pythagorean theorem and all. But why? Why did I do that? Well, remember, I have the derivative of arc sine as 1 over cosine of y. So what I want to do is I just want to substitute out cosine of y. And so off to the side here, I'm going to say, okay, cosine of y. Well, remember, SOHCAHTOA, cosine is the side adjacent over the hypotenuse. So my cosine of y is the square root of 1 minus x squared. That's the side adjacent here to y, divided by 1. And obviously dividing by the 1 is trivial, right? So I can go ahead and I can replace cosine of y with the square root of 1 minus x squared. And there, my friends, is the derivative of arc sine. And you can see this here. So here is the derivative rule of arc sine. If I differentiate arc sine, that is going to be 1 over the square root of 1 minus x squared. Now, if I have a function u inside of arc sine, say something like 2x. Like what if it was arc sine of 2x? Okay, I would have to treat that as a u and then multiply times the derivative of the inside. So I just want to point out the chain rule derivative, which is right here, right next to it. So notice it's the same exact structure, except instead of x I have u, but I also have to multiply, right, times u prime. Now, another way, a simplified form of writing this, which you may enjoy, is just moving that u prime into the numerator. So this would be u prime divided by the square root of 1 minus u squared. That's the derivative of arc sine. Okay? You don't necessarily have to memorize these two derivative rules. I would just stick with memorizing the first column here, and just know that if you have if you have an input that is a function itself, you have to multiply times that derivative and execute the chain rule, that's what these are. Cosine inverse. The beautiful thing about arc cosine is it's the same exact thing as sine. It's the same thing. except whenever we take a derivative of a co, we always have a negative. So again, I want you to see, do you see how it's the exact same thing? It's the same thing, except there is a negative out front. Okay, same exact thing, except we have a negative. So the simplified form, again, I'm just going to put that u prime into the numerator, and we have this format. That's a u minus u squared. Okay? All right, and then last but not least, we have arctan, and arctan looks similar. It is a fraction. I do have 1 over 1 plus x squared. So notice the similarity in the structure, except I don't have a square root and it's a plus instead of a negative. Okay, these are the three most common. There are derivative functions for cosecant, secant, and secant, cosecant, and cotangent. Arc, that is, arc, secant, arc, cotangent, arc, cosecant. But they rarely, if ever, come up on the AP test. So I'm going to leave those off. Okay. If that is important to you or your instructor, if you're watching this video and you're not my student, then I would go ahead and look up those derivative rules. You can easily Google them and find those, and the application is going to be just the same. Okay. All right, and then chain rule. Let me jot this down. Y prime is equal to u prime over 1 plus u squared. Okay, so now that we have our derivative rules, let's go ahead and put this into practice. These three are, again, something I would put on the flashcards. I would add to your flashcard ring, and then go ahead and spend your sleepless nights memorizing those. All right, example 2. Differentiate g of y is equal to arctan 2y minus 1. Okay, and I am differentiating with respect to y, so I don't really have to worry about implicitly differentiating. This is just defined in terms of y. So the derivative of arctan is 1 over 1 plus x squared. Now, in this case, I don't have an x. My u is 2y minus 1. 2y minus 1, and that quantity is squared. Okay, so whatever is there is squared, and because that's differentiable in and itself, I'm going to multiply now times the derivative of that, which is 2. Okay, which is 2. So there's your derivative. That's it. And if we wanted to go ahead and clean this up, we could. We could move the 2 into the numerator, plus 1 plus, I could expand this. What is this? 4y squared minus 4y plus 1. So let's make this plus 2. There we go. Okay, so there's g prime of y. Example 3. Differentiate f of x is equal to arcsine square root of x. Okay, I'm going to go ahead and I am going to use my arcsine derivative rule, which is 1 over the square root of 1 minus x squared. And again, in this case, I have a u. There's a function there, so that's the square root of x squared, and which we'll clean up in a second, times the derivative of this, times the derivative. Well, the derivative of the square root of x is 1 over 2 root x. Okay, and again, if you're struggling with that, just represent it as power 1/2 and use the power rule, and you'll end up with that. Okay, so let's go ahead and clean this up. So this gives us 1 over, let's say 2 square root of 1 minus x times the square root of x. Which I guess you could, why not? Move that in, we'll distribute those, so x minus x squared. Okay, and that's about as far as I would take that. Alright, so there's the derivative. Example 4. Differentiate h of t is equal to cosine inverse of natural log of t. Ooh, okay, alright, this one looks fun. So h prime of t is equal to, arc cosine is 1 over, and we have a negative. It's the same thing as arcsine. So 1 minus whatever is inside of the arc cosine quantity squared. So I have natural log of t squared, okay, times the derivative of the inside. And the derivative of the natural log of t is 1 over t. Okay, not too bad, not too bad. And let's just go ahead. Negative 1 divided by t times square root of 1 minus natural log of t, all of that squared. All of that squared. Not much we can do with that. Okay, so there's three examples of differentiating arc tan and arc sine and arc cosine. Here is an example for you. Please pause the video. I want you to go ahead. I want you to differentiate this example. All right, hopefully you have tried this one. The derivative is v prime of t is equal to 1 over square root of 1 minus 3x to the 4th squared times the derivative of 3x to the 4th, which would give you 12x cubed. Okay, and then if we went ahead and cleaned this up, you would have 12x cubed in your numerator over the square root of 1 minus 9x to the power of 8. Remember that 3x to the 4th squared is 3x to the 4th times 3x to the 4th. So that gives you 3 times 3, which is 9. X to the 4th times x to the 4th is 8. Both of those terms get the exponent, okay? All right. The next thing that I want to do with you here is look at example number 6, and that is review writing the equation of a line tangent to the function. And here they give us a function which is defined as arctan of 3x when x is equal to 1/3. So if you're going to go ahead and write the equation of a line, you first need a point. Now I know that my x value is 1/3. They give us this, but I don't know what f of 1/3 is. So let me go ahead and quickly find that. 3 times 1/3. 3 times 1/3, that's just 1. So tan inverse of 1, and that's going to be pi over 4. Pi over 4. Okay, so that is my y value, pi fourths. Awesome. I have my point. Not bad. Step 2. What's my slope? What's my slope at the point? Well, I'm going to have to go ahead and I'm going to have to differentiate. So first, I need to find f prime of x. Okay, arctan. Well, that's 1 over 1 plus x squared. Again, in this instance, I don't have just x. I have a u in there. U is equal to 3x. So this is 3x quantity squared times the derivative of the inside, which is 3. And I'll just clean this up. And we get 1 plus 9x squared. Okay, so there is arctan. And what I'm going to do now is I'm going to find, okay, f prime of 1/3. So let me plug in 1/3 here. And it looks like we get 3 over 1 plus 9 times 1/3 squared, which gives us 1/9. So 1 plus 9 times 1/9, that's just going to be 1. And we get 3/2. There it is. Not bad. Okay, so that's our slope. That's our slope. 3 over 2. 3 over 2. Okay, I have my point. I have my slope. So here is our equation. Y minus pi fourths, which is equal to 3/2 x minus 1/3. There's our equation. Okay, I'm going to go ahead and cover higher order derivatives in another video. So that's going to do it for this video on derivatives of inverse trig. Give me a thumbs up, like it, subscribe so you can see the next video on higher order derivatives. Catch you in the next one.